Now, Bernoulli tries to explain the concept of maximum likelihood estimation to Agatha. As you can see, maximum likelihood estimation is a bit more involved compared to the traditional machine learning algorithm. So it has a variety of concepts that are interconnected. So that's something we're going to see how we connect all the dots. Like what is likelihood? We're going to understand how that connects to Bernoulli distribution, which is the reason we have chosen Jacob Bernoulli to explain this algorithm. And then we look at what is log likelihood, and then we'll see how log likelihood is connected to cross entropy, and which is then related to chain rule, which is then related to gradient descent. Right? To quickly recap what has happened so far, we are going to see, as you can see, Agatha reached out to Bernoulli to kind of understand how machine learning can help her grandson figure out what is the best GMAT score that he can aim for in order to get admission into Carnegie Mellon, Tepper University for its MBA program. Right? And then we also already seen what exactly is logistic regression, how exactly logistic regression will work, the kind of data set Agatha brought to the table. So we're going to quickly recap what those are, and we're going to pick it up once Bernoulli came up with the equation, which explains the coefficients. And we're going to, in this discussion, we're going to see exactly how those coefficients were obtained in using all these techniques where maximum likelihood estimation plays a significant role. Right? Now, if you remember, so this is the problem that we had. So we had the GMAT score as input variable, and we are trying to figure out, given the GMAT score of a candidate, we have the output variable, which is admission status yes or no, accepted or rejected. Right? And then what Agatha did was she collected this data, and she had this data of GMAT scores and whether that particular student got admitted or rejected. And Bernoulli said he can come up with an algorithm, logistic regression, that can figure out what is the cutoff score that is required to have 95% chance of getting into the university, 90% chance, 50% chance, 60% chance. That's what we've discussed in the earlier part of the episode. Right? And then when Agatha asked, is this related to linear regression? Bernoulli says, somewhat. It is a classification algorithm. It's not exactly trying to predict the output variable, which is continuous variable in the case of linear regression. Here we're dealing with a different type of output variable. And Bernoulli said, this is the equation, minus 6.7 plus 0.012 into GMAT score. And this is where we stopped. Now, Agatha has an interesting question, right? She was trying to understand how did those coefficients come about? How did we get minus 6.7 and 0.012? That's what Agatha is asking. How does the training happen for logistic regression? Is this similar to linear regression? How exactly does it learn the coefficient values? To which Bernoulli said, it uses a technique called maximum likelihood estimation that finds the coefficients of input variables that ensure the maximum likelihood of seeing the probability values in the output variable. Now, as you can see, we have introduced a term called likelihood. And Agatha wants to understand that. What is this likelihood? Is it the same as probability? Most of us think it is the same. Likelihood, probability, English way, you see that both of them kind of are related to the same thing. Right? But Bernoulli says, not exactly. There is subtle difference between probability and likelihood function. As you can see from the figure here, probability values can be between 0 and 1. Likelihood values, however, need not sum up to 1. Right? So probability of you have successful events, unsuccessful events, they sum up to 1 in the case of probability. In the case of likelihood of different possible events need not sum up to 1. Right? And as you can see, in the case of probability, you are always looking at under a particular condition where the condition is fixed. You're looking at the probability of event happening. Right? Like say, for example, given that we have a fair coin, what is the probability of seeing a head? It is 0.5, given that it's already a fair coin. Right? Now, in the case of likelihood, we are going to reverse the question. Right? The event remains fixed. The event has already happened. Now, given that the event has happened, what is the probability of seeing that event? What is that condition that should be? Given that we have seen a sequence of coin tosses, is that coin a fair coin or not? As you can see, we flipped the coin or the question, as you can see here. Right? And that's what Bernoulli says. Let us take an example. Let us say I flipped a fair coin 5 times. What is the likelihood of seeing this sequence? The first 2 tosses were heads, next 2 tosses were tails, and the 5th and final toss is a head. What is the likelihood of seeing this? sequence. As most of you must be thinking, it should be 3 by 5, 0.6, right? So that's exactly what Agatha asked. But she also clarified, do you mean the probability of seeing a head? And she said that would be 0.6. Problem solved. Easy peasy, right? But then Bernoulli says, nope, I do not care about the probability of seeing a single head. That's not my question. My question is, what is the probability of this exact sequence appearing? There might be n number of sequences that might come up. It can be when you throw a coin 5 times, it can be all heads, it can be all tails, it can be 3 heads, 2 tails, 2 heads, 3 tails, 4 heads, 1 tail, 1 head, 4 tails. Like that, you have so many combinations. In fact, you have 32 combinations. Right? Out of all the 32 combinations, what is the likelihood? What is the probability of this exact sequence happening? Right? So probability of a sequence happening is nothing but likelihood of the sequence happening. Right? So then Agatha asks, okay, how do we calculate that? To which Bernoulli says, as we just discussed, there are 32 possible combinations that can show up when you throw a coin 5 times. Out of those 32, the probability of seeing the sequence is 1 by 32. And how do we calculate that? As you can see, because each of these tosses are independent, you can see that we are looking at 1 by 2, which is the probability of, let us say, if we calculate for this sequence, right? Well, probability of seeing a head, which is 1 by 2. Again, 1 by 2. Probability of seeing a tail, 1 by 2. Again, 1 by 2 and 1 by 2. Right? So 1 by 2 multiplied 5 times, you have 1 by 2 to the power of 5, which is nothing 1 by 32, which is nothing but 0.03. Now, how do I interpret 0.03? If you repeat the above experiment with 100 people, right? You ask 100 people to throw the coin 5 times, and you then record all the sequences that they've seen. Out of those 100 people, approximately 3 people would be seeing this exact sequence: 2 heads followed by 2 tails, and then followed by a head. That's how you interpret this probability, which is 3%, 3.125%. Okay, now Agatha says, okay, this is good. But why did you separate out the multiplication with respect to heads and tails? If you notice, instead of just writing 1 by 2 to the power of 5, I've written it differently. 1 by 2 to the power of 3 and 1 by 2 to the power of 2. Right? Why did you separate it? Because as you can see, this 3 corresponds to number of heads we see in the sequence. Right? And this 2 corresponds to number of tails that we see in the sequence. Okay, why did we do this? That's what Agatha is asking. And to which Bernoulli says, this is because if I have to generalize this formula for any event that has only 2 outcomes, right? One outcome is P, other outcome is Q. Where P corresponds to the probability of seeing outcome 1, and Q corresponds to the probability of seeing outcome 2. Right? We get a distribution of probabilities where there are only 2 possible outcomes, and this is similar to our problem. What is our problem? We have the output variable, which is admission status, accepted or rejected. There are only 2 possible outcomes. And we have a distribution of probabilities. You have the first student in the data set not getting admitted, second student admitted, third student not admitted, fourth student admitted. Like that, similar to the coin toss scenario, we also have, let us say we have 100 students example, we have 100 probability values, and that is nothing but a distribution, right? And this is exactly how you can generalize it. As you can see from this formula notation, just like how we had P equal to 1 by 2 earlier, 1 by 2. So if I just put in the values here, so this is 1 by 2 to the power of 3 and 1 by 2 to the power of 2. Going back to our coin toss example. Now, what's 1 by 2 corresponds to probability of success. Because there are only 2 events, we consider one event as success, one event as failure. You can choose whichever one way you want to denote it, right? And then N corresponds to the total number of trials. So how many times did we toss the coin? 5 times, right? And K corresponds to how many times we saw heads. Right? As you can see, the sequence is heads, heads, tail, tail, and head. Right? As you can see, we saw head 3 times. If you consider that as a successful event, then we are going to get K value as 3, and N minus K, this is going to be nothing but 5 minus 3, which is going to be 2. And that's exactly what we wrote earlier. Right? So this formula came from observation. Most of the formulas in probability, they come from performing experiments, and you're generalizing that. And that's exactly how we have got this. Right? And K corresponds to number of times you see head here. And this is similar to our problem. That's what Bernoulli is saying. To which Agatha says, what exactly is the distribution you're talking about? Right? What do you mean by this distribution? Right? What does that mean? Why is that popping up in this discussion about maximum likelihood estimation? And this is where we come to our second checkpoint in this journey, which is Bernoulli distribution. Now, Bernoulli proudly says, this is my distribution, a special case of distribution. where you're going to throw the coin only once, right? And that distribution is called Bernoulli distribution. In the previous example, we throw the coin 5 times, right? But what Bernoulli is saying is there is a miniature version of the previous experiment. You just throw the coin once, and whatever you see as outcome, it can be a head or a tail. Now that probability value, if you just repeat that experiment once, right, only one trial, and if you note down that value, probability value, that is nothing but a Bernoulli distribution, right? And the output variable in our problem, in any classification problem, follows a Bernoulli distribution, because think of each student as independent, as a separate experiment. You're not, the same student is not taking GMAT multiple times and applying to the university. You have different students spread across different countries taking GMAT and applying to that university. So each student is a separate Bernoulli trial, right? And you have the outcome of this student's attempt. Either he's getting accepted or rejected, just like head or tail. Right? Either he can get accepted or rejected. But here we are having a combination of Bernoulli trials in your data set. Right? And because it's a combination of Bernoulli trials, all the probability values are nothing but whether they're getting accepted or rejected, all the zeros and ones, yes or no, admission status. That distribution is nothing but a Bernoulli distribution. If you think of this as the admission column, right? And you have, let us say this is the first student, second student, third student, right? So fourth student, like that, you have all their admission statuses. And this is nothing but a Bernoulli distribution, because we're talking about probabilities. And because there is only one trial, because each student is separate, right? Each student is, the second student's efforts are not dependent on the first student's efforts. The first student GMAT score is not influencing any other student's GMAT score. That's the reason we say the number of trials as 1, and that's where n value gets substituted with 1. So p to the power of k, q to the power of 1 minus k, and we call this as the Bernoulli distribution form. This is where the likelihood concept gets extended to Bernoulli distribution. To which Agatha says, okay, now I understand why you are featuring so prominently in the discussion surrounding logistic regression. That's why we've chosen Bernoulli as a person to explain. How is this connected to our problem? Okay, I understand Bernoulli distribution coming to target variable and all this, but I was asking you about how does the algorithm learn the coefficients? And you are going ahead talking to me about maximal likelihood estimation, and then you told me about likelihood, and now we're talking about Bernoulli distribution. So where are you headed? To which Bernoulli says, I'm coming there. Just like the coin example, we need to find out for what value of coefficients will we see the maximum value for the below likelihood function. Basically, what's happening is we are answering this question. Given the data set, how much weightage should we give to the GMAT score so that the distribution that we already have in the target variable in our data set actually happens? Right? So it is something similar. It is, as we discussed in the one of the earlier slides, we are looking at the likelihood of this distribution, the data set actually happening. Right? In order for that likelihood to be maximum, meaning to be absolutely certain, what should be the coefficient value? So as you can see, this is a question that is in reverse. Earlier, in the case of probability, we already have a condition. Under the condition, we're going to calculate probability. Now what we are saying, we already have the probability distribution. We have the probability distribution, which is the actual target variable distribution. Right? Now, given that we already have that probability distribution, what should be the coefficient values? How much importance should we give to the input variable so that this distribution actually happens? Right? And that is how it is connected. And as you can see, because each student's scores are independent, each student's admission status is independent, we're going to denote using this Greek notation pi, right? Using PR of vi, meaning nothing, but we are just going to, just like how we calculated the coin tosses, multiplied all those 1/2s, we are going to do the same thing here. And that is how we are going to connect this to Bernoulli distribution, right? And now we have an equation. And what do we do when we have an equation in machine learning algorithms? We are going to differentiate it. And here's where we're going to differentiate the Bernoulli equation and find the combination of values when the slope is 0, which is similar to what we have done with linear regression. That's what Agatha is asking, as she has done it in episode 1. And Bernoulli says, precisely, from the earlier discussion, we know that likelihood of a Bernoulli distribution is like this. If I just convert this, right, into the notation that we've seen earlier, this is nothing but p to the power of y into 1 minus p to the power of 1 minus y. That's a px into q 1 minus x, that was our earlier formula, and I just replaced q with 1 minus p and x in the exponent power with y. Right? And then if I just have to calculate this, right? Whenever a student's status is admitted, in which case y equal to 1, right? In which case the likelihood will be nothing but p. If the student's value is 0, if it's not accepted, then it is going to be 1 minus p. Right? And if I generalize this is how it is going to look like. If I just substitute this, then this is the formula, this is the equation that we talk as the likelihood equation, and the algorithm tries to maximize this likelihood. It maximizes likelihood, find out those coefficient values where this whole value becomes the highest. That for each sample in the data set, we're going to substitute the values, calculate pi, yi, and then try to see how this, at what coefficient value will we get the maximum likelihood value for this particular equation. And now Agatha has one more question. So what does p to the power of y represent? What is y here? Right? As you can see, pi is the predicted probability value. So your algorithm, right? If you guys remember from the earlier discussion, we had the natural logarithm odds ratio equal to W0 plus W1x. That's how the probability value is predicted by the algorithm, right? So pi is the predicted probability, it's a predicted output variable, and yi is the actual output variable value. So actual value is nothing but 1 or 0, either we're admitted or rejected. Whereas predicted value can be between 0 to 1, because it can be between, it can be 0.1, 0.2, 0.3, 0.4, right? And that is how these two values are represented here. And if you also notice, this y also represents, right, in a Bernoulli trial, what does y represent? Number of successes, right? And as you can see, it is very easy to find out. Let us take one student, right, whose name is Nitin, right? And his data is Bernoulli trial, right? So 720, let us say he got admitted, okay? And as you can see, Bernoulli trial is related to just one sample. How many successes are we looking at? Only one success, because he successfully got admitted. How many failures are we looking at? 0, right? And this is the beauty of Bernoulli distribution in the case of Logistic Regression problem, right? This y, which is the actual value, represents number of successes and number of failures, right? Actual number of successes, as you can see, right? Now what we do, we just do p of 1 here, and this value will be 0. And we have another student's name, let us say Kiran, right? And then let us say he got a score of 650, and he's rejected. And here, how many successes are we looking at? 0. This value will be 0. And how many failures are we looking at? 1. And this value will be 1. Okay, because 1 minus y, which is nothing but 1 minus 0, which is nothing but 1. So it will be 1 minus p. Okay, so that is how this likelihood function perfectly summarizes the problem that we're trying to solve with Logistic Regression algorithm. Okay, now, this is what Bernoulli says. Y here represents whether the student got admitted or rejected. Remember, in a Bernoulli trial, there are only 2 outcomes, 0 or 1. And y represents one of these 2 values. And that's the reason why y represents the number of successes, right, for any given sample. Okay, and this is how the whole equation looks like, right? And that is what Agatha is also saying. Since the number of successes equivalent to value of y, we have replaced the parameter k in the Bernoulli distribution, as I just said, with y here. Is my understanding correct? To which Bernoulli says that is correct. Now we need to maximize the below likelihood function L. However, there is a problem. Not everything is hunky-dory. This concept looks good, but there's a problem with this equation. Any idea what the problem is? Agatha is asking, what is the problem? What's the problem with this equation? We have the equation, why can't we just go ahead and maximize it? This is where we come across the third concept in this learning path, which is log likelihood. And what Bernoulli says is, the problem is that since the probability value is so small, between 0 to 1, it will take a long time for the algorithm to learn small values, right? After every, with respect to gradient descent and other techniques, it has to run through iterations. It has to look at data set. We were talking about maybe thousands of rows, millions of rows in the data set. And it will take a long time for it to adjust, because we're trying to reduce 0.6 into 0.5554 and then 0.5567, like that. You are going to keep on reducing it. It will take a lot of time, right? And whenever we are confused, whenever we cannot handle those miniature small values, that's where we take the help of logarithms. Right? We apply logarithms precisely in those scenarios, right? Because once we apply logarithm, what it will do, it will spread out the scale of the fractional values, and it will make it easy for the algorithm to converge, because now it is going to deal with actual numbers, rational numbers, right? And then Agatha has a question. If I apply log to this, wouldn't that deviate from our goal of finding the optimal coefficients? You are now changing the rules of the game. That earlier you said L, right? We are going to maximize the maximize the likelihood. Now we are saying we are not going to maximize the likelihood. We are going to maximize the log likelihood. Wouldn't that deviate? Should we again renormalize the coefficients and all that, right? And Bernoulli says no. Be it the original likelihood curve, which is this curve, or the log version of it, which is I. Let us call the original curve as L, right? And I is the natural logarithm of that L. We are still trying to find out the coefficient values when the slope of the likelihood function is 0. So be it L here, which is this value, we are trying to come up to this value, or the log version of it, right? In both cases, we are still trying to find out this value, the value where the slope is 0, right? And so in order to make our calculations easy, we have approximated by applying log, but that doesn't really deviate from the original intention, which is to find out the coefficients that result in the maximum likelihood value. We just need to find out what combination of values, what combination of coefficient values actually result in hitting that point that I just circled in red here. Right? So we're good. We're good with maximizing log likelihood. Right? And that summarizes the log likelihood aspect of it. So now we apply log on both sides. We apply now that we are good to go ahead with log likelihood. We apply the log on both sides. And here is where you need to again brush up your logarithm formulas that some of you might have been introduced during your childhood. That's where we are going to apply the natural logarithm here. And then remember, ln of AB is equal to ln of A plus ln of B, multiplication, right? So you can actually split them out into summative terms after applying the natural logarithm. And similarly, ln of A power B is nothing but B ln A, right? Now applying these two rules, we have the ln, that we have two terms here. This is A and this is B that you see here. And then we are going to separate them out as we discussed, right? It's going to be ln of A plus ln of B. We separate them out. And now we have A power B kind of notation, right? Now what we do, we just do yi ln pi plus 1 minus yi ln 1 minus pi. So this is the equation that we are going to now find out the maximum value for this equation. So this is nothing but the log likelihood equation. Right? Now that is what Agatha is asking. Now we just have to maximize this function. Isn't that right? Right? And this is where there is one more problem. Right? So that's where cross entropy comes in. Now what is the problem? Now we have to maximize it, but there is always a but when it comes to, not everything is so straightforward in machine learning. Right? But we know gradient descent, how it works. It works better when we are trying to minimize something rather than maximizing it. Instead of maximizing a function to which case we don't know where the upper limit can be. It can be anything, upper limit. Right? Programming wise, it becomes easy, or even mathematically, when you look at calculations, it becomes easy. Rather than maximizing it, we actually minimize that function. And how do we do that? We just minimize the negative of that log likelihood. Instead of maximizing log likelihood, positive log likelihood, we are going to minimize the negative log likelihood, which is the same, right? But the only advantage that we have is it becomes easy. Gradient descent, understand, okay, this is a similar problem, and we are going to get the results much faster, right? So minimizing the negative function, which is nothing but maximize the log likelihood. And this, as Agatha rightly guessed, is the popular cross entropy cost function. This is a cost function for logistic regression. Right? As you can see, minus yi, which is nothing but actual value, ln of pi, which is nothing but the predicted value, probability. Right? Plus 1 minus yi into ln 1 minus pi. Okay, so this is how we get the cross entropy cost function for logistic regression. And that's what he says. That's what Bernoulli says, correct? This is what is a popular cross entropy function. And we are going to now calculate the gradient for this cost function using the gradient descent technique. We're going to differentiate the below likelihood function with respect to the weights. We are going to calculate dou j, which is nothing but minus ln of L, by dou w naught, which is that equation, if you guys remember, minus 6.7 plus 0.012 into GMAT score. How did we get minus 6.7 and 0.012? Then we're going to differentiate the cost function with respect to weights W0 and W1. So dou J by dou W0 and dou J by dou W1. Now, you guys must be wondering, there is something wrong here. Not everything is so plain here, right? That's what Agatha is asking. Wait, this equation, you're saying we can differentiate with respect to those weights, but this equation doesn't have the weights. We don't have the terms W0 and W1. So how will the differentiation work? How are you going to differentiate this? That's a fair question, isn't it? So from where are we going to get this term? General differentiation works when you are differentiating with respect to that value. If W0, W1 is not there, if you're just applying differentiation directly here, dou J by dou W, right, this term will become 0. This term will also become 0 because there is no that term, right, directly seen in the equation. That's what Agatha is asking. But as you notice, that term is not directly here, but indirectly it is there. And what do you mean by indirectly? It is nothing but we already know in the previous discussion, ln of P I by 1 minus Pi, which is nothing but odds ratio as we discussed earlier, is equal to W0 plus W1x. Right? So it is lurking somewhere. It is there behind the scenes. We just need to dig it up. And that's exactly what Bernoulli says. And the way we dig it up is by actually throwing a chain. And that's where chain rule comes in. Chain rule lets you differentiate complex functions. The popular chain rule, calculus 101, that's exactly what we are going to do now in order to calculate these gradients. And now Agatha says, now this is another new concept. What is this chain rule? We are so close to the end of the tunnel that where did this chain come from? That brings us to the last but one milestone in this learning path. It's what exactly is chain rule. So Bernoulli says, when dealing with complex functions like our cost function here, chain rule allows us to break down complex functions into simpler functions and then differentiate. As you can see here, in order to differentiate a complex function which contains a subfunction, we actually differentiate the subfunction, inner function, and then we differentiate the outer function with respect to it. Right? Now, it looks a bit complicated. Right? So as you can see from the figure, kind of makes sense if you look at it. Dh by dt is equal to first, because h contains a function of x, we first differentiate with respect to the inner function dh by dx, and then dx by dt. And that will, you guys must be thinking we should be canceling things up, but that is not how differentiation works. That we are going to actually differentiate with respect to inner function and then get the outer function. Right? Now, Agatha asks, okay, this sounds theoretically fine, but can you just show an example for it? To which Bernoulli says, okay, let us take this function here. This is how we apply the chain rule. Let us take this complex function, ln of x squared minus 1. Okay, and how we apply the chain rule is first we differentiate the inner function, as we said, x squared minus 1, right? 1 by x squared minus 1, right? And then we are going to then differentiate the value ln of, so a simple formula is ln of x is equal to 1 by x, right? Because we are first differentiating x squared minus 1, we just said 1 by x squared minus 1. Right? And then we are going to differentiate this x squared minus 1, because this value we still need to differentiate, right? We're going to differentiate x squared minus 1, and that will be x squared minus 1 by dou x, right? So by dou x, and this value will be, as you can see here, 2x, right? And this is exactly what chain rule is. We go step by step, and this is exactly the concept behind deep learning also, backpropagation, chain rule concept. Okay? And that's what Bernoulli says, but then Agatha says, okay, this is good. We understood what this chain rule is, but how does it apply to a cost function? This looks like a toy example, but how does this work out for a cost function? To which Bernoulli says, let us first look at what exactly is at stake here. We have this equation, which is the equation that we already have seen, negative log likelihood, which we are trying to, for which we are trying to calculate the gradient. And we also have this term, this particular function, right, where we are going to calculate the probability. So this is nothing but we rearrange the terms with respect to natural logarithm odds ratio equal to alpha. Alpha is nothing but W0 plus W1x. This is the linear regression equation, right? We rearrange the terms and we get this. And this is nothing but sigmoid function, the popular sigmoid function. Right? This function we already have. So we know that this is a relation. This is where the logic discussion that we discussed earlier comes into picture. So we already observed the logic function links probabilities to linear regression equation through this equation. Now we already have the regression equation. So we have these three terms. Now we need to calculate the gradient. Right? So now Agatha also says, okay, this is complicated. Now we are not just dealing with one function, we're dealing with three different equations, three different gradients. Right? And to which Bernoulli says, we are going to simplify it. This is how we apply the chain rule here. We have these three functions. This is how we are going to do it. So we'll see the demonstration for with respect to W1, how we differentiate it. W0, also the process will be the same. Right? And this is where the chain rule comes. First, we're going to differentiate the negative log likelihood with respect to PI, predicted probability value. And then we're going to differentiate this equation, predicted probability value with respect to linear regression equation. And then we are going to differentiate this linear regression equation with respect to W1. And so this is how we are going to navigate this. To which Agatha says, so we need to calculate derivatives for each of the three components. Exactly. Right? And let us first differentiate the cost function, the most complicated one first, with respect to the predicted probability value PI. And remember the gradient for log function, which we already just discussed. Ln of k is equal to 1 by k. Now, what Bernoulli is saying is, this is what is actual cost function. Now we're going to differentiate. And we're going to differentiate it simply, right? So yi is a constant term here, dou by dou pi of ln of pi, right? And then similarly, 1 minus yi is also a constant term here, dou by dou pi of ln of 1 minus pi here, right? And then if I just do that, ln of pi is nothing but 1 by pi here. And then here, ln of 1 minus pi is nothing but 1 minus pi, applying chain rule, dou by dou pi of 1 minus pi is nothing but minus 1, right? And if I just rearrange the terms, this is how it will look like. This is the gradient of the cost function with respect to predicted probability value, pi, yi by pi minus 1 minus yi by 1 minus pi. Now, Agatha says that was easy. We did not really, we just used this one simple formula, ln of k equal to 1 by k, right? So what next? Which function are we going to take next? Second comes a slightly more complex function. Right? We differentiate the predicted probability value with respect to regression equation alpha. So dou pi by alpha. So before we differentiate, we are going to rearrange the terms. Right? So instead of the same equation can be written in this formula. Why? Because e power minus alpha is nothing but 1 by e power alpha. Right? And then if I do 1 by 1 plus 1 by e power alpha, right? So what we get is nothing but e power alpha by 1 plus e power alpha, which is exactly what is this term, right? So instead of writing e power alpha numerator denominator, I'm just going to put it in the denominator because this will make it easy for me to differentiate. That is how we got this equation here. Right? And then I'm going to apply dou alpha here. And one thing that you need to remember is this formula here, right? As you can see here, dou by dou k of 1 by k is equal to minus 1 by k squared, right? And then dou by dou k of ek equal to ek, e to the power of k, right? So that's exactly how you are looking at differentiating. Those are the classic differentiation concepts. If I just do that, right, then what I'm going to do, I'm going to just do, because 1 by k is nothing but minus 1 by k squared. So minus 1 by 1 plus e power minus alpha whole square. And then I'm going to just differentiate e power minus alpha, right? Dou by dou k of e power k is e power k again, because if you differentiate it again, it will be the same, because the rate of change of exponential function is always going to be the function value itself. It's e power minus alpha. And then because I'm also going to do for alpha minus alpha, differentiation is going to be minus 1. Right? If I just arrange these terms, if I multiply these terms, this is how I get it. Right? I just have this equation and then I multiply them. Then I'm going to get it as e power minus alpha in the numerator. The denominator I have 1 plus e power minus alpha whole square. Now what I do is, because I want to keep things simple, I'm going to rearrange the terms. I'm going to just write the numerator as 1 into e power minus alpha, and denominator I'm going to split them into 1 plus e power minus alpha and 1 plus e power minus alpha. And does it ring a bell? If you see this equation, this is nothing but pi into 1 minus pi. This is the equation for pi value, isn't it? If you guys remember here, that's the pi value is nothing but e power alpha by 1 plus e power alpha. And that's exactly what we got here. 1 by 1 plus e power minus alpha is nothing but pi, and that value is nothing but 1 minus pi. Right? So now this is the gradient for the second component in the cost function that we are trying to differentiate. That's a 2 down, 1 to go. We have two values. Earlier we had that fraction. Now we have this value for with respect to pi with respect to alpha. Now the final one is the easiest one. Finally, we differentiate the regression equation with respect to the weight W1. right? And this one is nothing but you just apply dou W1. Here you'll be getting the value as X, because W1 by dou W1 X by dou W1 is nothing but W1 X is a constant here, right? And then W1 by W1 is nothing but, as you can see, it is 1. Right? So I believe the next step, now we got the 3 gradients. I believe the next step is to multiply all these 3 gradients. That is precisely what we'll be doing. Now we multiply all the 3 gradients we have obtained using the chain rule. This is a chain rule, right? We have got the gradient with respect to predicted probability gradient with respect to alpha, and alpha gradient with respect to W1. Right? We just multiply all these values yi by pi. This is the one that we see here, right? And this is the one that we are looking at here, and this is the one that we have for this one here, right? And then we multiply that, and again we rearrange it. So yi by pi into 1 minus pi into x, right? So this particular term will be multiplied by these 3 terms here, right? And similarly, this term is also multiplied by 3 terms here. That's what you're saying. You're saying x, pi, and 1 minus pi. Right? And then what we are saying is the final gradient of the cost function, if I just do that, right, and if I just calculate it, and if there'll be the cancellations happening, these 2 terms will cancel. And finally, this is the gradient of the cost function with respect to W. This is what we set out. This is what we wanted to calculate, which is nothing but x into predicted probability value minus actual value. This is the gradient value with respect to W1. And with respect to W0, the value will be the same, except x value will be 1. If you repeat the same steps using with respect to W0, you'll get the exact same thing. The only difference is going to be, instead of dou Z by dou W1 by dou W1, we got x earlier for the third component. Right? And if you do it with respect to W0, it will be, the constant will be 1. Right? Just mathematical arrangement. That's it. Nothing much, nothing less. Right? And this is how we got the gradients. This is the light at the end of the tunnel that we were looking at. This is the end of the calculus adventure. Right? Now, what is it? Is it done? Did we get the coefficients? Not yet. We just calculated the gradient. Now we need to apply the gradient. And that's exactly where the final checkpoint comes, which is gradient descent. Just like linear regression algorithm, here also we're going to use the same gradient descent algorithm. The only difference is the gradient calculation. In the case of linear regression, gradient values are different. Here, the gradient values are different because it's a different cost function. Right? We are going to update the weights with the gradient using gradient descent algorithm, which will give the final coefficients that we have seen earlier. So step 1, just like linear regression, we are just going to randomly choose the weight values for the GMAT score aspect of it and the constant of the linear regression equation. And then it will calculate the gradient for the cost function. Right? This is how just like in the earlier slides we have seen, we have calculated the cost function, and it is going to use a learning rate, eta, and it is going to calculate the gradient. It will adjust the weights by subtracting the gradients, and then it will repeat the steps 2 and 3 till the time the cost function value is minimum, which is nothing but we are trying to minimize the log likelihood, which is nothing but we are trying to maximize the log likelihood. And minimize the negative log likelihood is equivalent to maximizing the positive log likelihood, which was our whole intention, because we want to ensure that the Bernoulli distribution that is there in the data set is upheld by what combination of, course, what is that hidden coefficient value in the data set that will ensure this probability distribution that we are seeing with respect to admission rate. Right? And this is how we get the final equation. Natural logarithm of odds ratio equal to minus 6.7 plus 0.012. This is how all this weight updation ultimately resulted in. This is how we got that final equation. This answers what Agatha was asking at the start of this discussion. Right? And Agatha says this indeed is a fascinating algorithm. Thanks much for explaining this in so much detail. Right, so with that, we come to the conclusion. As we have seen, we have covered the concept. As you see, where we have started and where we have ended. It all started with a simple coin toss, likelihood. And then we try to understand what likelihood has to do with Bernoulli distribution. We are trying to maximize the likelihood of the Bernoulli distribution of acceptance values in the data set. Right? In order to maximize it, we said, okay, logarithms will make it easy for us to perform calculations. That's where we took a log likelihood. And then we said minimizing a negative value is equivalent to maximizing a positive value. That's where cross entropy came into the picture, which is nothing but so negative log likelihood is cross entropy. And that is the cost function for logistic regression. And then we looked at how we calculate gradient with respect to weights using chain rule. And then finally, we applied the gradient descent. Once we got the gradient calculated with respect to weight using chain rule, we applied the gradient descent algorithm, and that's how we got the coefficient values. Hope you guys enjoyed the discussion as much as Bernoulli and Agatha did. And until next time, this is Sai signing off.